when we go say to a human, lock that or unlock that, it's not a PSU. Nope. I have to leave mine on in case there's a PSU alerts thing goes on. When we talk about, we just say, hey, we go up. If the room's not locked, we go into the room and then we lock the room. Okay? If it's go up and it is locked, then we can have a chance to wait. So, for example, you're at a big party or a concert, and the restroom. That's sort of the way. That's just sort of the way that sort of works, right? So now, it's important for us to note that there's no way to describe acquiring a lock that does not have more than one instruction. You have to say, is it locked? Yes or no. Okay, that's actually more than one assembly statement. Okay? But if it's not locked, lock it. So the malicious scheduler can come after us, can it? So if we try to roll our own and just do it in our software, we think we can do it. This is the code. This is actual C code that does what we want to do, except it doesn't work. If lock equals 0, load the value of lock from memory, do a compare against 0, look at the condition codes when we're done, and if the condition codes are set a particular way, perform the following action. Which we say lock equals my PID, which now it's sitting in a register, so now we have to go get load my PID from memory, bring it in, write it into the other register, and now we have to write that register back out to memory. That's even more steps than I++. Okay? Ouch. Here we want to give up a lock. It turns out that when we unlock something, do we want just anyone to unlock the bathroom door?
No.
Okay, that would be bad. So locks have an idea of ownership. And we need to think about that because when we get to semaphores, they do not have a concept of ownership. Okay. So you can only unlock a lock if you're the one that locked it. So now, someone asked a question about locks at the very beginning where I said we're going to get to that. Or I said, what if someone tried to unlock a lock they didn't lock? Okay. In XV6, that routine is called release. And if you try to unlock a lock you don't hold, it means something's gone horribly, horribly bad in our code. We have a bug of some kind. So guess what we do? We crash. Okay, if it was a user program, we would just terminate the user program. It's the operating system though, and the only way to stop the operating system by saying, hey, you're messed up, you can't continue to do anything, we just crash it. And we print out some information that hopefully you'll be able to figure out what went wrong. That's a concurrency bug. Okay? Every project from here on out has the opportunity for concurrency bugs. I guarantee you, we have 96 students in 333 this term, between the two sections. I guarantee that at least 90 of you are going to have concurrency bugs. Rare for people to go through and not have concurrency bugs. Probably 80 of you are going to need help from the lab, people in the labs, or me and the TAs. Did I mention at the very beginning, I think we did in the first class, if you're staring at a problem for an hour or more, you've already convinced yourself there's no problem. But you know there's a problem. At that point, you need to ask for help. Okay. But you can show your code to me and the TAs. So just do a make tar. Okay. And ship it to us. And we'll work on it. You'll continue to work on it as well. One of the things that we find, and this is kind of humorous, but there's a psychological reason for it to occur. Almost 50% of the time when somebody sends us their code, they send us a code and an email explaining what's going wrong. and they'll tell us what the error message is and everything like that. Okay? And then they'll press send, and then they'll go, crap, I know what went wrong. Because in order to write that email, you had to slow your brain down, didn't you? That's why the lab assistants, you go, I'm having this bug, they'll say, well, tell me what's going on. And if you say, I think it's in this code, you say, okay, tell me what this code is doing. They all got A's in this class. They know what that code is doing. Okay? They're not necessarily doing it for their benefit. They need to know exactly what you wrote, because you're probably going to write the code differently than they did. Okay? But the whole purpose is to get you to slow down so you don't make assumptions. Yeah, I just assume that line is correct. I've looked at it so many times, it's got to be correct. Just keep going. You know what? You're going to find a concurrency bug, and the first thing you're going to do is say, I'm an idiot. No, you're human. Do not beat yourselves up. Okay? A lot of the time we spend in the labs and in office hours is telling people it's okay to have bugs. We want you to have them at school so you can avoid them when you get a job. Okay? They're not embarrassing. You might think, I shouldn't have made that, but how many of you have done concurrent programming before? Just out of curiosity. How many of you have done concurrent programming in an operating system before? Recognize that. Okay? If you don't have bugs in Project 3, we say that you're not getting your money's worth. Okay, we have had people come to us and go like, well, I got Project 3 done. I didn't have any bugs. And we'll go, okay, got your code all turned in, great. Let's grab your code, put it in another directory, and let's put some bugs in it. Why? Well, tracking down concurrency bugs is hard. It's a specialized technique. Okay, it's a specialized technique. And practicing is how you get better. That's just the way it works, right? So those are the things that we're going to be working with you heavily on in the labs in particular, is they're going to be working with you on the techniques and in getting you to say, this is what my code does. Your code might be correct, by the way, because the bug might have occurred someplace else. Okay. It could be that you corrupted something, but you didn't discover it was corrupted until someplace else. So your operating system might crash, or your program might crash, but the bug isn't there. That's just where you discovered the bug. Isn't this fun? Okay. Have you guys had any of that where you had a function where you manipulated some data and you got it wrong? Like you left the null terminator off a string. And you got some other routine where everything goes bad, and you look at the code and you go, there's nothing wrong with this code. And the answer is yes, there's nothing wrong with that code, but there is something wrong with that code over there. Okay? All right, that's how concurrency bugs mostly feel. And we're going to see that. Okay, so I'm just giving you a heads up. We have had people, in spite of us talking like this, who have gone like 2 or 3 days without asking for help. Get an email that says, I've spent about 25 hours on this and I can't find it. You guys need to help me. And we're just like, oh man, you must hate us by now. More than you did before. Okay. So don't fall into that trap. When you start, if you want to do a concurrency bug and you're starting to, you don't find it with like in 5 minutes, we recommend you set a timer on your phone. Because has anyone ever started working on a bug at like 9 o'clock at night and go, well, I'm not finding it. I'm just going to take a break. It's 3 a.m.
Yeah.
Okay, was that a fun feeling?
No.
It's just like, this is a time work. Okay, those happen. And we're trying to tell you, so we want you to recognize that it could happen, and you need to find a technique, an egg timer or an alarm on your phone or something like that. Okay. Also, remember how like on the Slack channel and also in person, you can discuss algorithms all you want. You just can't write code. Okay. So it could be that you're really frustrated and you go like, okay, I'm going to take a break. But what I'm going to do in that break is I'm going to describe my problem on the Slack channel in case someone else has seen it and can describe to me at a high level how to fix it. They can't tell you how to write your code, They can say, oh, that's really a problem with this concept. I did it this way, which was wrong. I needed to do it this way. And you can look at that and go, oh, I'm doing it the wrong way. I should have done it that way. Okay? In the lab, we'll oftentimes write pseudocode up on the board, and someone will go, oh, I should have done it that way. And they re-implement it as that. And they're like, oh, my code now works. Because sometimes we look at your code, and it should work. But there might be a subtle bug that even we can't find. They do exist. So that's really, really, really subtle bugs. And as a result, we say, hey, what I want you to do is like, I'm not sure if there's something wrong with that. What I want you to do is use this other algorithm, because I know that algorithm works. And then we can take a look at the code. The bug is still there. We know it's not in that code, but it might fix your bug. Use this other algorithm. And so we'll talk about algorithms and swapping out algorithms all the time. Okay? Just be prepared. All right? So, what we tried to do today is start talking about concurrency and some of the problems, the big problems that we see once we start doing concurrent programming. XV6 is concurrent. User programs are not. The operating system is concurrent. Okay? It's because we have more than one CPU and also because of interrupts. So there's a lot of concurrency going on at any one point in time. Debugging, you're going to find some specialized techniques we'll help you with. Okay? How many of you use breakpoints in GDB? How many of you put a breakpoint in and found that you had to actually go through, hit continue about 10,000 times before the time you wanted it? Okay? There's different ways to do it. Okay, so you don't have to do that. Who knows about watch points? Okay, watch points are a way to say, hey, watch this location of memory, and if it ever does block, because you program it, like let's say it's ever outside of this range, which is what you're looking for with the breakpoint. Okay, if it's ever outside that range, then stop. In which case you don't have to hit continue 10,000 times, right? It'll automatically just go by it saying, I don't need to stop, I don't need to stop, I don't need to stop. Oh, stop. Okay, so that's a conditional breakpoint. And then there's some other techniques. Like, you're just like, I just need to let it go until it crashes. Well, the way we crash XV6, if you're running it inside GDB, just go over to your GDB window, hit Control-C, and now you're in GDB. Okay? So you don't have to go, I got to keep, I think it's in this routine, it's going to be called, like the scheduler. Schedule's called every 10 milliseconds. Okay. It usually takes about a minute of my program to run before it crashes. How many time interrupts could occur in that time? A lot. But you're going to have to type continue. How many more interrupts are going to occur because you had to slow down to do those continues? Okay. So it can be very, very frustrating. Very frustrating. So this is what I wanted to talk about today. We're going to go into specific techniques, locks and condition variables next time. And then we're going to go into semaphores and talk a bit about well-known problems in concurrency control and how they're solved. In particular, I think we're going to talk reader-writer problem, not reader-writer, producer-consumer problem, and the Dunning philosopher's problem. Then after the midterm, after we talk about virtual memory, we're going to come back and look at some more. Okay, because they're just, all they are just prototypes. Simplifications of problems that occur in the real world. Okay? I don't think any of us are going to go out there and write the killer app to allow 5 philosophers to eat. But we can couch our problem a lot of the times in terms of philosophers trying to eat. And if we know how to fix the philosopher's problem in the simple setting, it helps us to understand the bigger, more complex problem and gives us a chance to solve that. Okay? Questions? Guess what? We are actually done, even though we have 15 minutes. Okay, so what I'm saying is, if you have questions, I'm here. I'm a captive audience. Okay. So last time, are there questions? Wait a second, we got a question.
For program 2, do we have to implement a time user program as well?
Yes, you're implementing a time user program, and we tell you not to write any new system calls. You're going to be able to write the time user program without implementing any new system calls. But the PS user program, you're going to have to implement the system calls.
Okay.
Okay. And that, in particular in that, you're going to go into the sysproc and do a sys_getprocs routine. And then you're going to have to call a helper function that you're going to have to put into proc.c because you're going to have to look at the p table. And you can only look at that in proc.c, which means that you need to have that globally available. So you're going to put your function prototype in defs.h. And that's that last step in the adding a system call that you didn't have to do in project 1.
Cool.
But I would put it in the list. Okay. When you add new user programs, you create like ps.c, immediately edit runoff.list, go to the end of it, and add ps.c. Okay. We had we typically have 5 or 6 people that submit project 2 without doing the steps that we tell them to do, and as a result, they don't turn in all their code. Okay, and unfortunately, everyone else was able to do that. So it turns out letting you turn your code in late is not fair. So we don't let you do that. Okay, the process we have you go through when you do a make dist test, it copies all your stuff into a subdirectory and then compiles it. And if it successfully compiles, that means it will successfully compile for us because that's the data it's going to send in. It uses runoff.list. So if you compile it, do make dist test, and it says, hey, this file's not found, and you go, yes it was, I was just using it. Okay? That means it's not in runoff.list. Okay? You're going to have header files as well. There's going to be one called uproc.h. You have to put that in runoff.list as well. Okay? Has anyone run into that yet? Okay. But some of you will, and you'll know how to fix it. Some of you will run into it, not remember how to fix it, so you send us emails, we'll tell you how to fix it. But if you turn it in broken code, where we have to run a test to make sure that your code works, if we can't compile it, can we run the test? How many points do you get for that test? We're not going to read your code and say, yeah, I think that would work. No, that's just not the way it works. Okay? Okay, anything else? Sure.
You can add like 4 system columns. Is that what you
Yeah, somewhere around 4 or 5 system calls. Okay. Now, like get PID just touches the currently running process. So get UID and get GID, just read it out of the process, so you can do that in sys_get UID. Set UID, however, modifies the process. Okay, so you're going to have to put a helper function in proc.c, lock the p table, go find it, and update it. In the get routines, okay, we would really like for you to use a helper function, but we're not going to force you to. Okay, we usually let you do that. But the sets all have to have proper concurrency control. If we're going to do real concurrency control, even on the gets, we should be putting a helper in proc.c so that we have access to the lock. Then we read the data. Then we unlock it in case someone's trying to change it. But we don't have a set set UID for a different process in this class. But in a regular operating system, you would. Okay, so we're simplifying it. So we would prefer that you did it, use concurrency control all the time. But on the gets, get UID and get GID, we're going to be very forgiving in our grading. We're not going to be forgiving in those sets. You have to do those correctly. All right. Other questions? Did I answer your question? I should have asked first. Sorry about that. I didn't mean to be dismissive.
Yep.
I apologize. Okay. Any other questions?